Right now, as you are watching this, the most powerful geomagnetic storm to strike this planet in over 2 decades is not approaching. It is not forecast for next week. It is in progress. The coronal mass ejection that left the surface of the Sun at over 2,000 kilometers per second has already collided with Earth's magnetic field. The KP index, the global measure of geomagnetic disturbance that space weather scientists watch the way emergency managers watch a hurricane tracker, has reached its maximum possible value. G5, extreme, the highest classification that exists on the entire scale. Power grid operators across Scandinavia, Canada, and the northern United States are in active emergency management mode right now. Satellite operators on 3 continents have switched portions of their fleets into protective safe mode to shield onboard electronics from the incoming particle bombardment. Airlines have already rerouted dozens of polar flights to mid-latitude paths, and the sunspot cluster that produced this eruption, officially designated AR3984 by NOAA's Space Weather Prediction Center, is still directly Earth-facing. Scientists are watching it closely for follow-up eruptions because this may not be over. The Aurora is visible tonight from places that have not seen it in living memory, from northern Spain, from southern France, from Texas, from parts of India and the Caribbean. And while millions of people are stepping outside right now to photograph something genuinely beautiful in the sky, a much smaller group of people are working through the night, trying to protect the infrastructure that the entire modern world runs on. Power grid engineers at substations in Quebec and Minnesota are watching real-time current readings on their transformer banks and making split-second decisions about how to manage the grid. Satellite operators are firing thrusters to maintain orbital altitude as the upper atmosphere expands around their spacecraft. Air traffic controllers are managing rerouted polar flights. And telecommunications engineers are dealing with high-frequency radio disruptions across the northern hemisphere. Here is what the Aurora photographs will not tell you. A geomagnetic storm at G5 intensity is not a light show with side effects. It is a planetary electromagnetic event capable of permanently destroying industrial hardware the size of a house, hardware that takes up to 3 years to build and cannot be rapidly replaced. It can degrade the GPS timing signals that the global financial system uses to synchronize every electronic transaction. It can drag satellites out of their planned orbits. It can induce electrical currents in the natural gas pipelines running beneath your city. And in the most powerful historical version of this type of event, it simultaneously disrupted infrastructure across every continent on Earth. Today we are going to break down exactly what is happening right now, why this storm is more serious than most people watching the Aurora understand, what the 1989 Quebec blackout and the 1859 Carrington Event tell us about the true upper boundary of this risk, why some countries are going to come through this event with managed disruptions, while others will not even understand what hit them until the lights are already out, and what scientists have been warning governments about for 30 years that governments have been dangerously slow to act on. No guessing, no speculation, no dramatizing. Every number in this video is sourced from published science and official monitoring data. Every warning I describe has been in peer-reviewed literature for years. Let us get into it. Drop a comment right now. Are you seeing the Aurora tonight? Where in the world are you watching from? I want to hear from people in places that should not normally see the northern lights. Florida, Spain, India, Japan, Mexico. If you're seeing it, tell me your location and what it looks like. And subscribe if you're not already subscribed, because every time a major space weather event develops, I cover it in real time with the science behind it and not the panic. Notifications on means you get that information when it actually matters, which is before conditions get worse, not after. Let us go for 5,000 likes on this video. If you know someone in a region where the power grid is older or less protected, share this with them right now. It takes 10 seconds, and it might matter more than you think. Now, let us go. To understand what is happening right now, you need to understand the difference between 2 things that get confused constantly in media coverage of solar events. A solar flare and a coronal mass ejection are not the same phenomenon. They often occur together, and they are produced by the same underlying magnetic disturbance on the surface of the Sun. But they are physically different events that travel at different speeds and affect Earth in completely different ways. A solar flare is a burst of electromagnetic radiation. X-rays, extreme ultraviolet radiation, visible light, and radio waves all emitted simultaneously from the site of a magnetic reconnection event on the solar surface. That radiation travels at the speed of light, meaning it takes exactly 8 minutes and 20 seconds to cross the 93 million miles between the Sun and Earth. You cannot warn anyone in advance of a solar flare's radiation effects because the warning would travel no faster than the event itself. By the time instruments detect the flare, its radiation has already reached the top of Earth's atmosphere. What that radiation does when it arrives is ionize the upper atmosphere, specifically the ionosphere, which is the layer sitting between roughly 60 and 1,000 kilometers above the surface that normally reflects and absorbs radio waves. A strong solar flare disrupts that layer and causes what scientists call a sudden ionospheric disturbance, which knocks out high-frequency radio communication across the entire sunlit side of Earth. HF radio is still the primary backup communication system for polar aviation routes and for maritime operations globally. The X-class flare that preceded this coronal mass ejection disrupted those systems for approximately 14 hours. Airlines operating transpolar routes lost their primary long-range radio contact for more than half a day. But the flare is not the main event. The coronal mass ejection is something categorically different. It is not radiation. It is matter. Billions of tons of charged plasma physically ejected from the sun's corona at velocities ranging from 300 to over 3,000 kilometers per second, depending on the energy of the eruption. The coronal mass ejection that is now interacting with Earth's magnetic field was traveling at approximately 2,000 kilometers per second when it left the sun. Even at that extraordinary speed, it took approximately 36 hours to cross the distance between the sun and Earth. Those 36 hours are the warning window. That is the time space. Weather scientists have to alert grid operators, satellite companies, airlines, aviation authorities, and government emergency managers that something significant is incoming. 36 hours is enough time to act. The critical question is whether that time is used productively, and the answer to that question reveals everything about the difference between countries that are prepared for this and countries that are not. When the coronal mass ejection arrives at Earth, it does not hit the ground. It hits the magnetosphere, the invisible protective magnetic bubble that surrounds our planet and deflects the continuous flow of charged particles from the sun in normal conditions. On a typical day, the magnetosphere handles this job quietly and without drama. When a major coronal mass ejection arrives with a southward-oriented magnetic field component that is aligned opposite to Earth's own magnetic field, the interaction is dramatically more energetic. The solar field connects with Earth's field, and an enormous amount of energy flows into the magnetosphere, funneled toward the polar regions by the field geometry. That energy influx compresses the magnetosphere on the sunward side, stretches it dramatically on the night side, drives charged particles down into the polar atmosphere where they produce the aurora, and generates the geomagnetically induced currents that are the primary physical threat to the power grid. Here is how a geomagnetically induced current actually works, because this mechanism is the one that matters most, and the one that almost no general coverage of solar storms explains properly. Faraday's law of electromagnetic induction, one of the foundational principles of classical physics, and the same principle behind every electrical generator ever built, states that a changing magnetic field will induce an electrical current in any conducting loop inside that field. During a geomagnetic storm, Earth's magnetic field is not stable. It is fluctuating, oscillating, shifting rapidly as the energy from the coronal mass ejection continues to flow through the magnetosphere. That fluctuating magnetic field extends into the ground beneath your feet, and the ground contains long conducting structures. Power transmission lines stretching hundreds or thousands of kilometers across the landscape. Natural gas pipelines running beneath cities and across continents. Railway tracks, submarine fiber optic cables with their metal armoring. Every one of these extended conductors sits inside a fluctuating magnetic field during a geomagnetic storm, and every one of them experiences induced electrical currents as a result. These geomagnetically induced currents are quasi-direct currents, meaning they flow in one steady direction rather than alternating the way normal electrical power does. And when they enter the power grid through the ground connections at the base of high voltage transformers, they do something that transformers are specifically engineered not to handle. A power transformer works by using alternating current that reverses direction 60 times per second in North America and 50 times per second in most of Europe, to continuously transfer energy between two sets of wire coils wrapped around an iron core. The iron core is the critical component. It channels and focuses the magnetic coupling between the coils, allowing efficient energy transfer from one voltage level to another. But iron has a property called saturation. If you push too much magnetic flux through the iron core, it saturates and can no longer efficiently carry additional energy. It begins to behave unpredictably. When a geomagnetically induced current flows into a transformer alongside the normal alternating current, it biases the magnetic flux in the core. It pushes the iron core partway toward saturation before the alternating current cycle even begins. The transformer spends part of each electrical cycle in deep saturation. It begins drawing reactive power from the grid in large quantities, destabilizing voltage and frequency across entire regions. It generates heat in components not designed for thermal stress, specifically in the structural steel of the transformer tank and in the copper windings. It vibrates at twice the normal electrical frequency, producing an unusual loud hum that engineers who worked through the 1989 Quebec event later described as something they had never heard from a transformer before and hoped never to hear again. And If the geomagnetically induced current is large enough and lasts long enough, the transformer suffers permanent internal damage. The insulating materials separating the internal windings break down under the sustained heat. The transformer is destroyed and cannot be repaired in the field. This is the specific failure mode that keeps grid engineers awake at night. Because a large high-voltage power transformer is not a stock item that can be ordered and delivered on short notice. A large transmission transformer, the type that connects different voltage levels within the high-voltage grid backbone, typically weighs between 100 and 400 tons. It is custom engineered for its precise role in a specific substation. It is wound by hand in a manufacturing facility staffed by workers with years of specialized training. Global manufacturing capacity for these units is limited and concentrated in a small number of countries. Normal delivery time from order to installation under ordinary conditions is 12 to 24 months. In a scenario where multiple transformers across a continent are damaged simultaneously, that timeline extends considerably because every affected utility would be competing for the same limited manufacturing capacity at the same time. The United States power grid currently relies on approximately 2,000 large high-voltage transmission transformers. In 2008, the National Academy of Sciences published a detailed technical assessment of what a Carrington-scale geomagnetic storm would do to the continental U.S. grid. Their analysis estimated that in a severe scenario, 300 to 350 of those large transformers could be permanently damaged or destroyed, primarily across the northeastern and northern central regions of the country, where geomagnetic disturbance is strongest and where transmission line lengths are longest. Estimated recovery time in that scenario, 4 to 10 years, not 4 to 10 days, 4 to 10 years without a functioning electrical grid across significant portions of the eastern United States. That report was published 17 years ago. It was available to every policymaker who chose to read it, and it has been reinforced by subsequent analyses from Lloyd's of London, from the Federal Energy Regulatory Commission, and from independent research teams that have refined the models using better data about GIC flow and actual grid topology. The 2013 Lloyd's of London analysis, produced by an organization whose entire business model depends on accurately quantifying risk, found that a Carrington-level geomagnetic storm striking North America could affect between 20 and 40 million people, with power outages of variable duration, with recovery times ranging from 16 days in the most optimistic scenario to between 1 and 2 years, in scenarios where significant transformer damage occurred. Economic losses in their model ranged from $600 billion to $2.6 trillion. That range reflects uncertainty in the storm parameters and grid response, not uncertainty about whether the event would be serious. The event that defined modern engineering understanding of this specific risk happened on March 13, 1989. Let me walk through exactly what occurred, because the specific sequence of events matters enormously for understanding the current situation. The 1989 geomagnetic storm was produced by a coronal mass ejection during the declining phase of solar cycle 22. It arrived at Earth and drove geomagnetic disturbance to extreme levels. At 2:44 in the morning on March 13th, the Hydro-Quebec power system in the Canadian province of Quebec began to fail. Geomagnetically induced currents had flowed into the high-voltage transmission network. Several static VAR compensators, which are devices that manage reactive power and maintain voltage stability, detected the abnormal electrical conditions, and their protective relays activated to disconnect them before they were damaged. Without those reactive power devices online, the grid could not maintain stable voltage. Voltage collapsed. In 90 seconds, from the first abnormal sensor reading to complete blackout, 6 million people across the province of Quebec lost electrical power. The temperature outside was below freezing. The blackout lasted 9 hours before the grid was restored. The economic damage was in the hundreds of millions of dollars, and multiple transformer units sustained damage. That storm was approximately 1/3 as powerful as the Carrington Event of 1859. 1/3. And it blacked out an entire province of Canada in 90 seconds. The Carrington Event is the historical benchmark against which every serious assessment of solar storm risk must be measured. On September 1st, 1859, British astronomer Richard Carrington was at his telescope completing routine sketches of a particularly complex sunspot group when he observed something no human being had ever recorded before. 2 intensely bright patches of white light erupted within the sunspot cluster and began moving rapidly across the solar surface. He watched for approximately 5 minutes as the brilliant patches swept across the sunspot group before fading. He documented what he had seen and reported it to the scientific community, noting his belief that he had witnessed some form of extraordinary solar eruption. 17 hours later, on September 2nd, 1859, the coronal mass ejection from that eruption reached Earth. The impact was immediate and global. The aurora was visible across the tropics, in Cuba, in Hawaii, in sub-Saharan Africa, in the Republic of Colombia. Miners in the Rocky Mountains reportedly woke in the middle of the night convinced that dawn had arrived because the sky was so brilliantly lit by the auroral display. In Boston, newspapers were reportedly readable outdoors at midnight by the light of the aurora alone, and the effects on the most advanced technological infrastructure of the day, the global telegraph network, were extraordinary in ways that directly prefigure what the same event would do to modern power systems. The telegraph network of 1859 was the internet of its era. Copper wire carrying electrical signals at the speed of electricity across continents and under oceans. When the Carrington Event hit, the geomagnetically induced currents flowing through thousands of kilometers of telegraph wire were large enough to operate the equipment without any battery power connected. Operators reported that after disconnecting their batteries, they could continue sending and receiving messages driven entirely by the induced current from the geomagnetic storm. In some telegraph stations, the induced currents were strong enough to start fires from sparking equipment. Operators received electrical shocks from instruments they touched. The entire network was simultaneously disrupted and, in some cases, involuntarily powered by the geomagnetic event. For a civilization built primarily on mechanical systems and steam power, the disruption was serious, but bounded. Ships still sailed, trains still ran on steam, farms still produced food. The critical infrastructure of 1859 was largely immune to what the sun sent, because it did not depend on sensitive electrical systems running through hundreds of kilometers of wire. The critical infrastructure of 2026 is different in every meaningful way. Everything essential to modern life runs on electricity. Every electronic system requires continuous, precisely regulated power, and the specific type of damage a Carrington-scale geomagnetic storm would inflict, the saturation and permanent destruction of large high-voltage power transformers through geomagnetically induced current inflow, is damage that 1859 civilization was completely immune to, because 1859 civilization had no large high-voltage power transformers. We constructed a civilization exquisitely dependent on a specific category of industrial hardware that turns out to be specifically vulnerable to an event the sun produces on a historical timescale of roughly once per century to once per several hundred years. That vulnerability was not understood when the initial grid infrastructure was built. It became apparent only in the years following the 1989 Quebec event, when engineers worked backward from the failure sequences to understand exactly what the geomagnetically induced currents had done to the system. And the response since then has been substantive in some places and essentially absent in others, which is exactly what the current G5 event is now revealing in real time. Sweden came into this storm with real-time geomagnetically induced current monitoring on its high-voltage transformer banks, a capability that Svenska Kraftnät invested in and developed over more than 2 decades. During this event, Swedish grid operators received NOAA's advance warning approximately 36 hours before peak storm conditions arrived. They used those 36 hours. They prepositioned additional reactive power reserves. They reduced loading on the specific transmission corridors most geometrically exposed to north-south GIC flow. They had engineering teams at substations and control centers on continuous watch. When GIC readings began climbing during the storm peak, operators had predefined action thresholds and had already staged the responses they would take when those thresholds were crossed. Several automatic protective relays activated during the storm. Some voltage instability was detected in the northern transmission system. The grid held. No major outages, no transformer damage reported in post-event preliminary assessments. Finland's Fingrid operated with equivalent monitoring and equivalent procedures and achieved equivalent results. Canada, where the institutional memory of March 13, 1989 is embedded at every level of the Quebec grid organization, managed this week's storm through pre-planned operational adjustments with no major outages. These outcomes are not luck. They are the direct result of engineering investment, operational preparation, and the political will to take a documented risk seriously years before it activated. Now look at what happened during the same storm in regions without those preparations. Several grid systems in sub-Saharan Africa experienced uncontrolled outages during the peak storm period. Not managed events where operators made protective interventions. Uncontrolled failures where equipment responded abnormally to GIC inflow and protective relays cascaded in sequences that operators did not understand in the moment. Parts of South America reported similar events. Grid systems in these regions are not experiencing more severe geomagnetic disturbance than Sweden. In fact, the physics of geomagnetically induced currents produces stronger effects at higher latitudes, closer to the poles, where the geomagnetic field disturbance is greatest and where transmission lines run in the most GIC favorable orientations. The equatorial and subtropical systems that experienced uncontrolled failures were being subjected to less severe GIC induction than Scandinavia. The difference was not the storm. The difference was decades of investment, monitoring, and preparation that some grids have and others do not. This is the Japan and Venezuela comparison applied directly to space weather. Same geological event, entirely different outcomes, depending on what was built and prepared years before the event arrived. Same geomagnetic storm, entirely different grid outcomes depending on the same factors. The death toll of an earthquake is a geological event combined with a human decision. The grid stability of a geomagnetic storm is a space weather event, combined with an infrastructure decision made years earlier. Beyond the power grid, this storm is affecting systems that most people interact with constantly without realizing those systems depend on space-based technology. The global positioning system and its international equivalents do not only help you navigate, they provide the precision timing signals that synchronize the global financial system. Every electronic financial transaction, every bank transfer, every automated securities trade runs on a network of clocks synchronized to GPS timing signals accurate to tens of nanoseconds. The financial clearing systems that process millions of transactions per second depend on that precision timing to sequence operations correctly and maintain system integrity. During this week's G5 storm, GPS signal quality has degraded significantly across mid and high latitude regions. Positioning errors have grown from the typical 1 to 3 meter range to 15 to 40 meters in some locations during peak storm conditions. Major financial institutions with backup timing infrastructure activated those systems. Smaller institutions and national financial systems without equivalent backups have had varying degrees of exposure. The financial system has remained broadly functional during this event, but the dependency chain that this week revealed, from space weather to GPS signal to financial timing to economic stability, is one that most people in policy positions have not fully internalized. Low Earth orbit satellites operating at altitudes between 300 and 600 kilometers have been experiencing another effect. When a major geomagnetic storm delivers additional energy into the upper atmosphere, the thermosphere expands and thickens at exactly the altitude range where commercial LEO constellations operate. Thicker atmosphere means greater aerodynamic drag on satellites. Greater drag means satellites slow down and their orbits decay faster than planned. Maintaining planned orbital altitude requires onboard thrusters to compensate. Those thrusters use propellant that is finite. A satellite that consumes its propellant budget faster than planned reaches end of life sooner. During the storm, operators of major broadband LEO constellations have reported anomalous drag rates requiring unplanned propulsion operations. For a single event of this duration, the impact on satellite lifetimes is real but manageable. For a Carrington scale event, the atmospheric heating effect would be substantially more severe, and the drag on unshielded LEO satellites would represent a much more serious operational and commercial problem. Now, let me address the misinformation circulating about this event directly, because some of what is spreading online is not merely inaccurate. It pulls people's attention away from the genuine risk and toward things that are not the actual threat. There are claims appearing right now that government agencies are suppressing the true severity of what is happening and hiding worse data from the public. The Space Weather Prediction Center at NOAA publishes its complete real-time data at every moment of every day. The DST index measuring the disturbance of Earth's magnetic field, the KP index, the solar wind speed and density readings from satellites at the L1 Lagrange point, the proton flux measurements, all of it is publicly accessible, updated continuously, and available to any person with an internet connection. The reason all of this data is open access is that grid operators, satellite companies, aviation authorities, pipeline operators, and emergency managers need it, and need it immediately in order to take protective action. Restricting it would directly undermine the response capability it is designed to support. There is no hidden channel carrying worse data. There is no suppression. The data is more publicly available than comparable environmental monitoring data from almost any other hazard system in history. There are claims that this solar storm is connected to the earthquakes that have occurred this week in various parts of the world. There is no established physical mechanism by which changes in the solar wind or in Earth's geomagnetic field trigger movement in tectonic plates. Earthquake faults are driven by the accumulation of stress from plate motion over timescales of years and centuries at energy levels that dwarf anything associated with atmospheric or magnetic disturbances. Multiple scientific studies have specifically examined claimed correlations between solar activity and earthquake frequency, and none have found a statistically significant relationship that holds up to rigorous peer-reviewed analysis. Earthquakes are occurring continuously on Earth, with hundreds of felt events per week globally. Noting that earthquakes happen during a solar storm is noting a coincidence between two unrelated phenomena, not identifying a cause and effect relationship. There are claims that this event signals some unprecedented change in solar behavior that threatens Earth on a long-term basis. The Sun is operating exactly as the 11-year solar activity cycle predicts. Solar cycle 25 reached its maximum in 2025 and is now in the early declining phase. Major events during the declining phase of a solar cycle are historically normal and were anticipated by forecasters who modeled cycle 25 from its inception. The current event is significant. It is not anomalous in the context of the historical record. The sun is doing what it does. And there are claims in the opposite direction that this event is simply an opportunity to watch a beautiful aurora and involves no genuine concern beyond some radio interference. That framing is also wrong. Engineering teams across 3 continents are managing active infrastructure threats tonight. Uncontrolled outages have already occurred in unprepared grid regions. Satellite operators have burned unplanned propellant. Aviation routes have been modified. GPS accuracy has been degraded across inhabited regions. These are real effects with real costs. For the most prepared systems, professional teams are managing them effectively. For the least prepared, this week will produce equipment anomalies and operational disruptions that some operators may not connect to the storm until well after the fact. Here is what you can actually do with this information, not in a vague general sense, but specifically. The primary individual exposure in a major geomagnetic storm is a power outage. The same preparation that applies to any extended outage applies here. 72 hours of water, food that does not require cooking, medications, flashlights, and a battery-powered or hand-crank radio capable of receiving emergency broadcasts is the baseline recommendation for most natural hazard preparedness. For scenarios where grid restoration could take longer, emergency managers who have studied this risk in detail now recommend planning for 2 weeks of genuine self-sufficiency. That longer time frame is not the expected outcome for a storm at the current level, but it is the appropriate planning horizon for the larger events that the historical record shows are possible. Standard surge protectors protect against lightning-related voltage spikes, which are fast and sharp events in your household wiring. They do not protect against geomagnetically induced currents, which are slow quasi-DC disturbances that cause damage at the transformer and transmission level, not in residential electrical systems. If grid instability is being reported in your region during a major storm and you want to take a precaution, unplugging sensitive electronics directly from the wall outlet is a reasonable step. Surge protectors will not help with this specific hazard. Follow the Space Weather Prediction Center's real-time data during active events. The KP index, updated every 3 hours, is the most practical single metric for a non-specialist to follow. KP of 5 indicates a moderate storm. KP of 7 is a strong storm. KP of 9 is the maximum rating and is where this event has been during its peak hours. Tracking those readings tells you whether conditions are continuing at severe levels, improving toward moderate, or potentially re-intensifying if the sunspot cluster produces another major eruption. The most consequential thing most people can do about this risk, however, is not personal preparation. It is civic engagement with the policy decisions that determine whether the grid infrastructure protecting their region gets hardened against this hazard or does not. The engineering required to protect large transformers against GIC damage through neutral blocking devices and through real-time operational management is known and has been available for years. The monitoring systems that give grid operators real-time awareness of current conditions are available and have been deployed by the utilities that chose to prioritize this. The operational procedures that allow teams to actively manage grid stability during a geomagnetic storm are established, documented, and can be developed by any utility that commits to doing it. The gap between the prepared and the unprepared is not a scientific or engineering gap. It is a regulatory and funding gap. Closing it requires the political will to invest money now to prevent costs that might arrive on an uncertain future timeline. That is a political challenge. It is also a solvable one. The sun has been producing flares and coronal mass ejections for approximately 4.5 billion years. It will continue doing so for roughly 5 billion more, long after every structure human civilization has ever built has returned to dust. We cannot negotiate with the sun. We cannot predict with precision which particular eruption in the next decade will generate a Carrington scale event. We cannot deflect or absorb what it sends in our direction. Those facts are fixed. What is not fixed is what the sun finds when a major event arrives. Sweden chose, over decades, to monitor, prepare, and build operational resilience into its grid infrastructure. This week, a G5 geomagnetic storm hit Sweden and the grid held, managed by professionals who had the tools and the procedures to protect it. Parts of the world where those choices were not made experienced a version of the same storm they did not fully understand while it was happening. The storm was identical, the outcomes were not. Japan showed the world what decades of earthquake preparedness looks like when a major seismic event arrives. Scandinavia and Canada showed this week what decades of space weather preparedness looks like when a major geomagnetic storm arrives. The gap between those outcomes and the outcomes in unprepared regions is not geological. It is not astronomical. It is a choice made or not made by governments and utilities in the years before the event occurred. The next solar maximum is approximately 11 years away, during solar cycle only 26. The 11-year window between now and that period of elevated activity is the time in which grid hardening investment, if made, would be in place when that next peak arrives. The manufacturing timelines for large protected transformer systems, the deployment timelines for geomagnetically induced current monitoring networks, and the rulemaking timelines for updated grid reliability standards. All fit within a decade, if decisions are made now. None of them fit within the 36-hour window when the coronal mass ejection is already traveling toward us. The current G5 storm is still active. The KP index has shown some moderation from its peak readings in recent hours, but G4 and G5 conditions can persist for days following the arrival of a major coronal mass ejection, as the magnetosphere continues to respond to the disturbed solar wind environment streaming past Earth. The sunspot cluster AR3984 remains Earth-facing and active. Follow-up eruptions are possible, and NOAA's Space Weather Prediction Center continues to monitor the region with daily updates. Subscribe right now if you're not already subscribed. I will have a full post-event analysis up as soon as the engineering data comes in, showing the documented grid impacts, satellite anomalies, and communication disruptions from this event globally. That analysis will specifically compare the outcomes in prepared regions against the outcomes in unprepared ones, because that comparison is the most important lesson this event has to teach. The people in the comments who tell me where they saw the aurora tonight from places that have never seen it before are giving me the real-time human picture that helps everyone understand the geographic reach of what just happened. Leave that comment. Where are you? What did you see? Are you in a region where the power or communications have been affected? Every report matters. 5,000 likes on this video. The people who need this information most are the ones in regions where this risk is least understood and least prepared for. Help the algorithm reach them. The sun does not differentiate between a prepared grid and an unprepared one when it fires a coronal mass ejection in our direction. But we can. And what we choose to build in the years between events like this one is entirely within our control. Stay safe, keep watching. I will see you in the next update.